So in the past couple of lectures, we talked about the modern recurrent neural networks, RSTM, GRUs. And we also started talking about attentions, general attention mechanisms, and self-attentions. So we'll summarize them and show that how attention is all you need. That's what transformers are built upon. And then we'll mostly talk about pre-training and BERT, for instance, and we'll end up with protein language models, okay? So let's end up with where we were last time. I think we were talked about position encoding before. I think that's where we start, right here. Okay. All right, so as we described it before, right? So you have learned how we start with attention and generalize them to general attention mechanisms. Then we progress them into self-attentions, right? You sort of have each input vector has an attention to each other input vectors, right? So that's what self-attention is about. So let's now think about what we have learned so far. We have learned RNNs, right? So we have learned RNNs that we see that we have okay, so we have learned about the RNNs. We have learned about the CNNs. So in the case of the CNNs, we have X1, X2, X3, X4, XT. And we learned that, again, we have these hidden layers. You know, let's say, I don't know how many of them are there, but you have basically this is kind of connection, right? Right? So if you compare, and then we have the self-attention, okay? So if you try to compare these three kind of architectures when modeling a protein, any sequence, okay, what do you see? What are the pros and cons here? So RNN is good at the fact that, you know, when you are reaching the last hidden unit, it's already finished looking at the whole sequence, right? You look at the whole sequence. That's sort of the pro, and the con is that you actually have to calculate this sequentially. There's no way to parallelize that. Okay, that's the pros and the con. What about CNN? Well, CNN, as you see, it has this relatively sparse convolutional kernels, right? A small convolutional kernels. So it sort of have a very limited input, right? If you look at each hidden layer or hidden node, it has very limited input. In this case, the kernel size is 3. And you sort of have to stack them, right? You sort of have to stack more and more, sort of to increase the receptive field width, right? So you have to stack into deeper and deeper CNN layers so that you can overcome the limitation that CNN is not looking at the whole sequence, right? But on the the other side, it's very parallelizable, right? That's CNN. What about self-attention? Self-attention, again, we are attending every input vector to another input vector, right? We have very global view of the whole sentence, and we are making things very parallelable, right? Because we'll see this block later on. Everything is taking different inputs independently, okay? If you look at the key, query, vector, all those are done by feed-forward neural networks, right? Actually, the only place we considered the order is where? In the attention layer. How did we consider the order information? We said that the self-attention, the attention layer itself is permutation invariant, right? Equivariant, actually, right? The final output, if you do a sum, is going to be invariant to the permutation. So where did we consider the order? Positional encoding, right? That's where we consider the order. That's the only place, okay? And the whole thing is very parallelizable. So now let's review again, right? So you may wonder, well, they all have pros and cons. Which one should I choose? Well, it turned out that in the 2017 paper, the authors found that you can simply use self-attentions. That's all you need for the tasks they are interested in. And they introduced this block called transformer block, and that they only use attention, self-attentions. And then there's, of course, cross-attention between encoder and decoder. But if we just look at the encoder itself, for instance, it will have multiple transformer blocks stacked together, okay? So let's review. We talked about each individual component of the transformer encoder in the last lecture. Now let's try to review it, right? You start with X, and then you do what? First, you have the positional encoding. We learned what is the rationale of introducing a positional encoding, and what do you desire from the positional encoding function, right? If you don't remember, please review those. One thing I didn't say was that, back then I was saying that, well, you could concatenate the input feature with the positional encoding, but actually in this paper, they actually just added the positional encoding to the feature vector, okay? It's very intriguing. Something to think about. Once positional encoding is added, we have self-attention, but we have multiple self-attention. Okay, so this is called multi-head self-attention, right? So the self-attention part is attends over all the vectors, right? Right? You have each xi, xj, right? Pair, but then you have like multiple parallel self-attention. Okay, so this is called multi-head, and then. And you will add a residual connection to improve the gradient flow. Remember, everything is about optimization, which relies on gradients, right? And then you will do a layer normalization to help the optimization so that the input to the next layer is always going to be zero mean and standard deviation, right? And then that's fed to the next MLP, right? And then this MLP is over each vector individually, so it's highly parallelizable. And then you will add a residual connection again, right? And then in the end, you do another layer normalization before you get the output, right? So you could have some kind of readout to get the output. So this is what a transformer block looks like, right? This is a single transformer block, which is the encoder alone, okay? There's only self-attention. This is within the encoder itself. I haven't introduced encoder decoder in this case, so there's no cross-attention between encoder and decoder yet, okay? All right, so let's look at something similar. What about the decoder, right? So what about the decoder side? So the decoder is very, similar. As a reminder, right, this decoder is basically like a language modeling task, right? So you start with y0, y1, y2, y3, and they're trying to predict y1, y2, y3. Right? Basically, person wearing hat N, if you want to start with this one. In other words, you always try to predict yt given y1, y0, y1 through y sub t minus 1. Okay, that's what language modeling is about. And this is the input and this is the output, okay? So we're still gonna use transformer block in this decoder, okay? We're gonna do it like 6 times, right? But in each transformer block, right? So the whole thing is called a transformer, right? And the use is a decoder that can be seen in the construction of the input, output, and the loss, right? And this transformer encoder consists of 6 transformer blocks which only use self-attentions. Again, you have something like here, right? And let's look at the transformer encoder block. Again, you have the positional encoding. But here, this is not multi-head, but masked multi-head, if something that we talked about before. And we'll talk about them again in some of the later lectures, but I hope you remember what this masked multi-head self-attention is about. That is basically, can someone remind me what the masked self-attention differs compared to the multi-head self-attention? Anyone? So remember, in the case of the decoder, we can only generate a text based on the past, a word based on the past, not the future. That's what the mask is about, okay? Let me see whether I can find it. It's way back. See, mask. Let's see. It's right here, yeah. So in the masked self-attention layer, remember that the way we generate this alignment, right? So you see that we have the query and the key, both are generated from the input, okay? But when we compare the query and the key, you see that query 0, right? For the query 0. It can only use key 0. It cannot use key 1 and key 2. And when you query Q1, you can only use key 0 and key 1. And when you do Q2, query 2, you can only use key 0, 1, and 2. In other words, you cannot look at the future vectors. Okay? So that's what the idea is about. And specifically, how we accomplish that is we force this alignment matrix to be minus infinity at these prohibited positions. Why minus infinity? Because the attention in the end is exponential of this alignment score, and exponential to the minus infinity gives you 0, right? Recall? Okay, so this is a masked self-attention. It is used for decoder, okay? Okay, so in other words, we are using the language modeling, right? P of xt given x1 through x sub t minus 1. That's what the language modeling is about, right? So now let's look at, then we do a layer normalization, and we're going to do some we're going to do some residual connections as well, right? Actually, there's something probably missing here, right? Because apparently we're adding something some. So I believe there is a residue. and it should be from the previous, right, layers. And then we do a normalization, layer normalization, MLP, and then we do another residue, and in the end we do an FC, okay? So most of the network is the same as a transformer encoder, but just keep in mind that in the decoder part, we cannot use the future, okay? So it's, in this sense, it's not bidirectional, okay? We'll emphasize this again, and then we have this multi-head attention attends over the transformer encoder outputs. Okay, so this is the cross attention, right? This is a cross attention between the encoder and the decoder. Okay, so please pay attention to these two differences. One is a masked multi-head self-attention compared to the self-attention. The other one is that we have the cross attention. Okay, between the encoder and the decoder. Okay. All right, so any questions so far? Okay, so we introduced all the elements in the previous lecture, and today we just started with a summary of these elements. So now let's look at the applications we talked about, the image captioning, right? So the input is an image and the output is a text describing the image, right? So we started with this example before, right? We gave one solution that used a CNN as the encoder, right? The initial encoder, and to convert these spatial features to this the raw image into the spatial features. Then you feed these features into transformer encoder. So something we have seen before, but pay attention that we actually just converted this two-dimensional features, or in the ordered way, right, into this vector, right? And then feed them directly to the transformer encoder, right? So apparently you need positional encoding to tell the transformer encoder where these pixels or elements were from, right? Because there was a spatial context. Now if you just use this flattened vector, that context is lost. You still need positional encoding. And that gives us the transformer encoder. The whole encoder consists of the CNN and the transformer encoder. Then we feed it into the transformer decoder, right? And this is the input, output, and we can train the thing, right? So this is one solution based on what we have learned previously, right? So so if you pay attention here is that we have not used any recurrence. There's no recurrence in this. We have the CNN, we have the self-attention. There's nothing involving the recurrence, okay? That was introduced in the recurrent neural network, LSTM or GRUs, right? There's no recurrence at all, so it's highly parallelizable, okay? But do we need CNNs at all? So that was a question I asked last time. So what is your answer now? Do I need CNNs at all? Can I just use the transformers and feed the raw image pixels directly to the transformer encoder? Can I do that? Well, I don't see a reason why not, right? Right? So you can, yes, you can. You can directly use the raw image and split them into pixels and feed to the transformer instead of the CNN encoded feature vectors. Okay, so you can do that. And this is some performance comparison. In the paper called "An image is worth 16 by 16 words," right? So this is the sort of one of the early work applying transformers for image recognition, right? So because starting from sequence processing or modeling, transformers is now entering other applications, including image and graph modeling, okay? And this is one of the early work for images, okay? And there are a lot of other things that are happening. This is from fast AI, which are, which produced something called DAL-E, DALL-E, which is basically a image generation software given a text. So the input is a text and the output is an image, okay? So in fact, just last week, Fast AI released the latest version, DAL-E version 3, and sorry, I think it's version 2. Anyway, it's the latest model. I strongly recommend you to look at that latest DAO-E that was released last week. So that was image generation prompted by a text. Okay. Any questions so far? Okay, so let's summarize, right? We started with attention, and we started with still using the recurrence in RNN, but allow attention to occur. So we allow them to attend to different parts of the input at every time step, right? So that actually allows for accuracy, but also explainability, right? That also helps us detect the bias in our neural network models, right? So we talked about that first. Then we sort of extracted a more general attention mechanism based on the early attentions, and then we actually could, it could be added on anything. It doesn't have to be on RNNs at all. And one of the key breakthrough is that we actually, can split input into key, query, and value, 3 vectors, through 3 learnable layers or matrices, right? And we use, keys and values in 2 different steps of this whole task, right? As an example, I said last time, if you're going to Google and find an answer about how many enrollments are there in the fall of 2022 at A&M College Station campus, it actually involves 2 steps. First, Google has to find the relevant home pages, web pages, and then, on those relevant pages, they need to extract the numbers you need, right? So there are actually 2 steps that don't utilize the input questions in the same way. So that is some intuitive understanding about why you want to use, this key and values separately. And then, so utilizing self-attention alone, right, and plus some layer normalization, some nonlinearity, right, we could introduce a block called transformer block that entirely, use self-attention without recurrence, without necessarily CNN, right? And it's highly scalable and highly parallelizable, right? So it's faster parallelizable training, it's larger model, better performance, and they are quickly replacing RNN and LSTMs, and it may be even replacing the convolutions, but I don't think, we should understand transformers in that superficial way, okay? So I don't think LSTMs or CNNs will be completely replaced by the transformers, okay? What are the shortcomings of transformers? Any ideas? Think about the attention, self-attention, right? Every input vector has to attend to every other input vector. So you have actually a huge self-attention matrix, right? Multiple times, alignment and attention. So it actually demands a lot of memory, right? That's one thing to think about. And one way to reduce the memory requirement is to, instead of use the full attention, you can use sparser attention, but that alone is a tricky question, right? Because, if you think about RNNs, CNNs, and self-attentions, right? So the self-attention actually has every vector attending to every other input vector, right? And that is actually one advantage of that. And I don't know whether you can design by principle how to, find a generalizable sparser self-attention or not, but I think that there's a lot of case-by-case scenario and theoretical proofs to be delved into.